Okay, so when we're addressing the topic of regular stochastic matrices, what makes a stochastic matrix regular? Aren't all matrices regular? Come on now. But, well, in linear algebra, regular doesn't always mean what you think it means. In this case, in this context, we have what exactly is regular about this matrix? So, a stochastic matrix is regular when some power of p has only positive non-zero integers. So we have this matrix, right? What happens when we bring this matrix to the power of 1, or any power really? You would notice that you don't have to actually do the math for this, by the way. You wanna know why? Because if you grab this matrix and you multiply it by itself, which indicates p squared, you're going to get a matrix that is going to consist of non-zero integers, and therefore this matrix is regular. Now, let's say we have a different matrix. Okay, so we're given this matrix where p has a 0 in row 2, column 2. So if we were to grab this matrix and multiply it by p, or if we were to bring p to any power, right, what's going to happen? Well, what we want to happen is we want for every power of p to be, for each entry to be a non-zero positive integer. So p squared is just going to be 0.50, 0.50, 1.00, and we're going to duplicate this because that's what it means to square the matrix. And by implementing basic matrix multiplication, we end up getting that our values become 0.75, 0.25, 1.00, oh, that's read 0.50, and we end up getting 0.50, and there we have it. And if we were to have this be p cubed, p to the fourth, or p to the fifth, all the entries are going to be non-zero positive integers, and therefore this matrix will be not just a stochastic matrix, but a regular stochastic matrix. Now, what happens when a matrix isn't regular? Okay, so say we're given this matrix. Now, what happens when we bring p to second power? What does that look like? So, it simply means that we're going to multiply the same matrix by itself, and here are the things that makes a matrix not regular. Do we know what we do? Do we know what they are? Well, every power of p, each entry within the matrix has to be a positive non-zero integer. So if you're taking p to several powers and there are zeros consistently, you get consistent zeros for each power, that indicates that the stochastic matrix is not regular. So let's perform our matrix multiplication for p squared. So let's see here. Okay. Let's multiply the first row. Let's multiply the first row by the first column, and we get 2/3. Now we're going to multiply the first row by the second column, and we get 0. And we're going to multiply the first row by the third column, and we get 1/3. Now let's do the same for the first row, the second row in the first column. And we're going to get 2/3. we're going to multiply the first row by the second column as well, the second row by the second column, and we get 1, and then we're going to grab the second row from the first matrix, multiply by the third row in the second matrix, and we get 1/3. We'll do the same for the third row in the first column, so that's 1/3. And we'll do it again for the third row in the second column. We get 0 and 1/3. And there you have it. So notice how we still have zeros after taking p to its second power. And if you were to take p to the third power or fourth power, you are bound to get zeros somewhere within the matrix, and therefore this stochastic matrix is not regular, as every power of p has zeros in the second column. Now, before I sign off in this video, I want to give you guys a challenge in the comments. So, when p is a regular stochastic matrix, we get the following pattern. We get p times x sub naught times p to the second power times x sub naught, and to the third power, and so on. And as the powers increase, it appears that in this Markov chain you approach a unique steady state matrix. Can you guys verify that in the comments? If you guys drop it down and it has my seal of approval, I'll pin the comment for everyone to see. But until then, good luck learning, guys.